will talk about this on a later occasion. This is the 22nd lecture and we are going to work out problem set 6. This is our problem session 5. The first problem that we are going to work out is 9.1. The problem says find the z, y, h and t parameters. Well, we have not done h and t yet in the class, so we will confine to z and y parameters of the networks shown in the figures. Some of the parameters may not be defined for particular circuit configurations. Now, what does that mean? Some of the parameters may not be defined. In other words, if that parameter blows up, if it goes to infinity, then it is not defined because we do not know what infinity is. For example, you look at the first network, we have a impedance Z, this is the 2 port, and you see that if I want to find out the Z parameters, for example, Z parameters Z11, keep this open and measure here, obviously it is infinity. Keep this open and measure at the input, Z11 is infinity, so is Z22, so is Z22, agreed. What about Z12? Z12 by definition, what is the definition? V1 by I2 with I1 equal to 0. So, if I connect a current source I2, pardon me, connect a current source and measure the voltage here, no current flows, the current source is ineffective and therefore what is infinite?
So V1 is 0, I2 is finite.
I2 is 0. Okay, so it is undefined and therefore Z12 is undefined, so is Z21, they are equal, they are reciprocal, and therefore we cannot find out the Z parameters of this. Our conclusion is Z parameters are not defined. Now, one of the things, as I go ahead, I will give you the tricks of the trade. One of the things that you can exercise is in such a network, instead of calculating Z11, Z22, Z12 every time you get a network, it may be useful to compare it with the T equivalent circuit that we had formulated. What is the T equivalent circuit in terms of Z parameters? Z11 minus Z12, Z12 and Z22 minus Z12. Remember this and compare with this. Okay, if you compare with this, there are many ways of identifying. For example, this we could identify as Z11 minus Z12. If I do that, then obviously Z12 is infinity. Infinity? Well, undefined. This is open. Infinity is also undefined. Okay, undefined. And Z22 minus Z12 is equal to 0 because there is a short circuit here. Okay, and therefore Z22 is also undefined or infinite, whatever the case may be, and Z11 minus Z12, well, this should also be infinity then. One of the ways is to compare the two equivalent circuits. We can do this comparison because the architecture of the given network is a 3-terminal one, correct? We can compare and immediately write down the Z parameters. On the other hand, if I want to find out the Y parameters of this, I will first find the easy way out. The easy way out is, you recall the equivalent circuit, pi equivalent circuit, which was in terms of the Y parameters, and this is Y22 plus Y12. By comparison, you notice that Y11 plus Y12 is equal to, no, the admittance 0, and therefore y11 is equal to minus y12. Similarly, this is also 0, therefore this is equal to y22. And what is minus y12? In comparison, this is equal to 1 by z, alright, and therefore our y matrix would be 1 by z, then minus 1 by z, minus 1 by z, 1 by z. Is that okay? These are the y parameters. And I did not calculate anything. Now let us see if the calculation gives the same thing. Suppose I want to find out y11, then what I do is I short circuit this, and therefore y11 would be simply 1 by z, as it is so. Similarly, y22 by symmetry is also 1 by z. To find y12 or y21, how do I do that? I2 equal to y21 V1 plus y22 V2. So y21 is I2 by V1. I connect a V1 here, I short circuit this and find I2. You must remember I2 enters the network, and therefore I2 by V1 under this condition obviously is equal to minus 1 by z, which is precisely what we have got here. Alright. These are extremely simple examples, but but ticklish, particularly when the parameters do not exist. For example, for this network, for the other network, okay, obviously y parameters would not exist. Why not? If you short circuit this, the admittance is infinity, and therefore if one of the admittance is infinity, the parameters are not defined. Alright, that is enough to take this network out of rail as far as y parameters are concerned. You could do that by comparing with the y parameter equivalent circuit, then one of y11 plus y12 would have been equal to y, or y22 plus y12, whichever you look at it, but you see minus y12 is infinity, and therefore y11 plus y12, even if that is finite, y11 must be infinity, and therefore the y parameters are not defined. What about z parameters? This is very simply found out if you compare this with the z parameters equivalent circuit, z11 minus z12, z22 minus z12, and this is z12. And therefore what are the z parameters?
Minus 1 by y.
1 by y. No, why minus?
Z11 is equal to minus 1 by y.
No, it is equal to plus 1 by y. z12 is y, 1 by y, and therefore all of them are equal. This is also one of the reasons why the y parameters do not exist. The determinant of this is infinity. This is a singular matrix, alright. The determinant is infinity, and you remember that y matrix or determinant is 0.
So it's a singular matrix.
That is, the matrix is singular, and you recall that y parameters are exactly the inverse of z parameters, or the other way around. The z parameters exist, but the determinant z is 0, and therefore the inverse does not exist. So the y parameters do not exist. You can only find out the z parameters of this. Let us do the third network here, which is a z1 and a z2. Once again, it is a 3-terminal network. Okay, I can apply the definition. Let us do that for a change. The definition z11, keep this open, so this would be simply equal to z1. Alright, keep this open, measure the impedance here. z22 would be, if this is open, then it is simply z2 plus z1. Now to find out z12, for example, z12 by definition is v1 by I2 with I1 equal to 0. So let us apply let us connect a current source I2 and measure the voltage V1 here. Obviously this will be I2 Z1 and therefore this is equal to Z1 and this must be equal to Z21 also. Alright. So our matrix shall be Z1 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 Z2 plus Z1. Alright. Now if you there are many ways of looking at it. Okay. This is one way. The other way is you compare this with the T equivalent circuit. Alright. In other words, you write Z11 minus Z12 equal to 0, short circuit. Z12, the shunt element, is obviously Z1 and Z22 minus Z12 equal to Z2. Alright. This element is 0, this is Z1 and this is Z22 minus Z12 and therefore it gives the same results, that is Z1, 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 Z1 plus Z2. This is the Z matrix. Okay. Alright. The third way of looking at this, let us exhaust these ways because this, it said that it sharpens the capabilities. If you can look at something from 3 or 4 different angles, every time it sharpens your capabilities, it gives you an enhanced tool to solve real life problems. Okay, I can look at this network as this network, let me use a different color. I can look at this network as this network which we have already solved, whose Z parameters are Z1, 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 Z1. Agreed? These are the Z parameters? No, only this, the pink colored network. Alright. Then what we have done is we have connected a Z2 in series at the output. Now what does Z2 affect? That is the question one is asking. Does it affect Z11? No, it does not, because this will be kept open. Does it affect Z12? No, because once again this will be kept open. Z12 or Z21, it does not matter. If I find Z12, I have to connect a current generator here, an impedance in series with current generator has no effect. Alright. It does not affect Z21, I connect a current generator here, what is here it does not matter because I have kept this open. Alright. It affects Z22, that is the only parameter it affects. How does it affect? It simply adds, and therefore the total network, now let me change the color, the total network therefore shall be, only thing that will be affected is Z22, so it is Z1 plus Z2 by inspection, no calculation, but this is a way of looking at it. It is a combination of two networks and this element simply affects Z22. We shall have occasions to solve networks in which we will not go through such calculations. We will simply say Z22 prime, that is of the composite network, is the original Z22 plus whatever is connected in series at the output. Okay. Now let us look at the Y parameters. Once again the network is Z1 and Z2. Let us do it in one or two different ways. Y11, if I apply the definition, short circuit this and then measure the input admittance, obviously this will be Y1 plus Y2, alright, where Y1 is 1 by Z1, Y2 is 1 by Z2. Y22, if I measure here with this shorted, obviously this will be simply Y22. Now can anybody tell me what would be Y12 without any calculation? No. Y12 or Y21, they will be equal. Minus 1 by the 2, that is correct. Minus 1 by, that is minus Y2. This negative sign was missing. How did he get that? Not by, you can calculate, you can also remember the pi equivalent circuit, that the shunt element, or the not shunt, bridging element between input and output that is minus y12, and therefore this would be minus y12 would be 1 by z2. So y12 is minus 1 by z2. Agreed? If you remember these ways of looking into a 3-terminal network, you see things will be very easy in future. The h and t parameters, well, we will leave them to you. We have not yet done in the class, and therefore if an occasion arises, if you have problems, you can ask me. We will go to 9.2. 9.2 we've solved the simple problem first, 1, and you will see that we will solve everything, almost everything by inspection. When we are forced to, we will go to methods other than inspection, all right. But here, as you will see, it will not require 3 ohms and 1 ohm. Okay. First, by inspection, Z11. If I keep this open, then Z11 is 1 parallel 5, that is 5 by 6 ohms. Z22 would be 1 plus 3 parallel 3. So this is equal to 1 plus 3 by 2, which is equal to 5 by 2. All right, 2.5 ohms. Z12, well, I know Z12 and Z21 shall be the same. Let's find out Z21. Z21 would be equal to V2 by I1 with I2 equal to 0. Let's calculate this. We have a I1 here, 1 ohm, 2, 3, and again 1, and our I2 is 0, therefore this is V2. What is this? This is also V2, because I2 is 0. So all that is required is to calculate this voltage, and you see how I calculate. The current would be I1 into 1 divided by 1 plus 2 plus 3, so 6. Okay, 6 multiplied by 3, that would be V2, multiplied by this resistance, that divided by V1, this will be Y21, no, that divided by I1. So it's simply half. I beg your pardon, this is Z21, which is equal to Z12. All right. Everything done by inspection. I didn't have to calculate Z12 because I noticed that the network is reciprocal, so they should be equal. All right. Let's look at the Y parameters and see if we can do the same thing by inspection. For Y parameters, let me draw the network again. 1, 2, 3, 1. For Y11, so you will have to short this. If I short this, then I get 1 plus 1 over, okay, this admittance in parallel with whatever admittance comes here, which is the reciprocal of impedance. So 2 plus 3 parallel 1, because this is shorted, 3 parallel 1, whatever the value is, you can now calculate. Is that clear? Have I done a mistake? No. I have to short circuit this, and so admittance 1, I am calculating admittance 1 plus whatever comes in parallel admittance. So it is reciprocal of impedance. Impedance is 2 plus the parallel combination of 3 and 1, and now you calculate. Similarly, Y22 would be equal to, you see, it starts with a resistance.
So won't it be 1 by 2 or something?
Pardon me?
So if we are taking the admittance, so won't it be 1 plus 1 by 2 parallel 1 by 4?
No, no. You see, I am calculating the impedance looking here. This is 2 plus the effective impedance of 3 and 1, which is 2 plus 3 parallel 1, and reciprocal of that adds to 1. Don't make such mistakes. Okay, one has to be careful. That's why I said nothing is routine here. Similarly, when you are calculating Y22, well, I have to keep this shorted. So this 1 ohm goes bad, it has no effect, and what I have is 1 divided by, why 1 divided by? Because 1 ohm comes in series. So I find the total impedance and take the reciprocal of that. So 1 plus 3 parallel 2, that's it. Okay, let's see Y21 and Y12. Once again my circuit is this 1, 2, then 3 and 1. Let's calculate Y21. Y21 by definition is I2 divided by V1 with V2 equal to 0. Okay. So I connect a V1 here and V2 equal to 0, so I connect a short circuit here, and this is the current I2. Alright, is that clear? Okay, this 1 ohm obviously goes out of the picture because it's in parallel with an ideal voltage source. So the current through this would be equal to V1 divided by 2 plus 3 parallel 1. And this current after going here divides into 2 parts.
3 by 4.
So 3 by 3 plus 1, but you have to multiply by a minus sign because I2 does not agree with the sign of this, and this divided by V1. Now you calculate. This will be Y21 equal to Y22. The numerical calculation you can perform. Alright. Here oh, Y12, I beg your pardon. How can I make such mistakes? Okay. One thing that I want to point out here is that you cannot do this by inspection. No way. There is not a single element between the input and the output. There are 2 elements and there is a junction in between. So that pi equivalent circuit or T equivalent circuit could not be applied here. Is this point clear?
So there's one resistance in series with the pi.
Okay.
Can't we have such?
What we could do is you could calculate the Y parameters of this by inspection, but this resistance affects Z22. It doesn't affect any of the Y parameters. So it's not a straightforward comparison with the equivalent circuit. You could also say this T 2, 3 and 1, that is a T equivalent, but this 1 affects Y11 not Z11. Is that clear? So one cannot apply equivalent circuits here, but wherever applicable you can do that. For example, the 9.2, the second problem. The second problem has this architecture. And you notice that it can be solved very easily by either T equivalent circuit or pi equivalent. Both are applicable here. Isn't that right?
Yes,
So we will not do this. Agreed? The third problem is a bit intricate. Third problem is a parallel T. The third problem is like this: R, R, C and C, C, R. Okay? To calculate the Z parameters and Y parameters without looking upon this network as a combination of 2 networks, obviously it's a parallel connection of 2 T networks, alright, but that does not help unless you apply matrix inversion, alright, and this also I shall leave to you.
Also we convert it into pi and make it simple.
You can convert each of them into a pi,
So there will be 3 parallels.
2 parallel pi networks.
No sir, but each one will be individually, all the 3 arms will be in parallel with each other, so it will be very
No, I didn't understand what you said.
So at the, when we replace each one of them by the pi,
Okay.
each arm would be in parallel with the respective arm of the other one. So it becomes.
That is correct. So
then it just
two
becomes one pi in the end.
pi's in parallel become 1 pi. Pi parallel pi is equal to pi, not in terms of numerical numbers, architecture, and therefore I can find the y parameters, but that is requires a conversion, and I assure you the labor involved is no less than the labor involved in making a node analysis or mesh analysis. It's almost the same amount of labor. One is matrix conversion, the other is matrix determinant, and both of them require almost the same amount of labor. However, whatever is convenient to you is a personal choice. Some people like blue sweater, some like red. It's exactly that. Okay, there's nothing to choose between. 9.3 and 9.4 are very interesting examples, and I want you to do this yourself. Very interesting example, very simple, but you have to find out how to proceed. That's about it. You have to figure out. So we will not discuss this. We will go to 9.5. 9.5, for the, it says for the circuit shown, the circuit is this. We have a network N, it's a 2-port network, port number 2 is terminated in RL. This is I2 and this is V2. This is V1 and this is I1. For the circuit shown, you have to find the voltage transfer ratio, voltage transfer function V2 by V1, and the input impedance Z1, which is equal to V1 by I1 under this condition, okay, in terms of Z parameters, of the network N and the load resistance RL. Okay. The problem is a 2-port which is terminated in a resistance to find out the voltage transfer function and the input impedance. Any suggestion as to how to proceed?
So we write it out the Z parameter like V1 and Z1 on I1 plus Z.
We write out the two equations,
Right. And then we say
and then manipulate.
Yes.
Okay. Any other approach?
So use RL as Z11 minus.
Can I use the T equivalent circuit here?
So rather than,
Mathematically
so rather
equivalent?
the pi equivalent.
You want the pi equivalent circuit? But the question says you have to work in terms
So
of
we
Z
can use,
parameters.
so it is 3 ports because the second terminal is.
Mayank, the question says you have to work in terms of Z parameters.
It's alright, so we can work in T also.
So we can work in T parameter. Can we use the T parameter equivalent circuit? T parameter is 3 terminal. What is the alternative? Alternative is to work with the equations. Alright. Suppose the network, now mind my words very carefully. Suppose the network had a bridging element here. Suppose we had something like this. Also, in addition to this RL, there was a bridging element here from here to here. Could we use the T parameter equivalent circuit? No, because then this element would have been short circuited. There is no such calamity, possibility of a calamity here, and therefore we can indeed use the T parameters. Alright, we can use, but as I said, it has to be used with caution. I have given you one situation where it cannot be used. Alright, now let's do it.
In that case, we would have used the definition.
Okay, let's use the definition, and I assure you the labor involved is nothing more, nothing less. It's almost the same.
So in that case, if there was some element across.
If there is some element, then we have to use the definition. Let us use definitions here also for this example. Let us see. Yes.
How do we know that I dash and P dash are short circuited?
How do you know that?
I dash and P prime are short circuited. Even if we apply the P.
No, you see, this is a truly 4-terminal network. What I was asking is, can we analyze this case by replacing n by its t parameter equivalent circuit? Alright? It happens that in this case we can. We can. But suppose our network was augmented like this, there was another impedance here, then we could not use the t parameter
So
equivalent circuit.
how do we know ki? So why can we assume that the parameter can satisfy any?
Oh, because the t parameter network satisfies the terminal equations V1 I1 V2 I2, that's all that matters. Alright, and there is nothing structurally, there is nothing to disobey these equations, and therefore we can replace.
But the basic assumption of t parameter is that this
Network is
I1
three
and
terminal.
I2 are short circuited.
No.
The second terminal and the fourth terminal are short circuited.
That is correct. That is correct. Basic assumption is this, and as I said, it's mathematical equivalence.
Yes, sir.
Now, working with the equations and working with the mathematical equivalence circuit should be the same. Okay, what I want to do is to use the equations, and I leave it to you to use the t parameter equivalent circuit and then verify that the results are the same. Alright. Okay, let us look at this. I shall solve this problem by yet another means a little later. I hope time permits. I have the network N, V1 I1, V2 I2, and there is a termination RL. So I write the equations, and n has been described by its z parameters. So I write the equations V1 equal to I1 Z11 plus I2 Z12. There should have been an objection to t parameter equivalent circuit, which none of you raised.
So we have to assume it's reciprocal.
You have to assume, if you are using a t parameter, then you have to assume that the network is reciprocal, which is not given, and therefore in theory there is an objection. So what I want to do is to solve it by assuming the equations and then show that if Z12 is equal to Z21, the t parameter equivalent circuit could also be used to calculate this, that they give the same results. That part, the second part, as I said, I leave it to you. Now how do you proceed with the equations? Equations are Z21 plus ZI2 Z22, and you notice that V2 and I2 are constrained by this load impedance. V2 is simply equal to minus I2 RL. Alright, that is the constraining equation. And if I have V2, therefore from this equation you know I1 in terms of I2. You know the ratio I2 by I1. Alright, is the point clear? You know the ratio I2 by I1. For example, you see that I2 by I1 is equal to Z21 divided by Z22 plus RL with a negative sign. Is this point clear? So I know I2 by I1, and if I know I2 by I1, then obviously I know V2 by V1. Okay, V2 by V1 is this divided by this, divide by I1. Okay, V2 by V1 would be equal to Z11 plus I2 by I1 Z12, Z21 plus I2 by I1 Z22. Agreed? No, I have made a mistake. What is the mistake? It's the other way around. This to the power minus 1. Okay, you simplify this, I will simply give you the final result. The final result is Z21RL divided by determinant Z plus Z11RL. Alright, this is V2 by V1 after simplification. The other question to be answered is V1 by I1. So the impedance Z1, which is equal to V1 by I1, obviously is Z11 if I take the original equation, V1 equal to I1 Z11 plus I2 Z12, it would be Z11 plus I2 by I1 Z12, which is equal to Z11 minus, substitute for I2 by I1, Z12 Z21 divided by Z22 plus RL. Oh, this stands for the determinant of Z, okay, and you see that determinant of Z once again shall come here. If you simplify this, you shall get Z1 as equal to Z22 plus RL. Then here we shall have Z11 Z22 plus Z11 RL minus Z12 Z21, which is equal to determinant Z plus Z11 RL divided by Z22 plus RL. All right. Okay. I want to go back to this equation.
So instead of dividing V2 by V1, we would have substituted I2 by I1 and first.
That's what we have done. That's what we have done. We haven't done anything else. We have substituted for I2 by I1. I want you to look at it, look at this network from a different angle. Let me draw the network, and again an alternative way. What we have is a voltage source here, V1, and RL. This is V2, and this current is I2. An alternative angle of looking at it. Suppose I apply Thevenin's theorem to the left of this. All right, Thevenin's theorem. Then what would be the equivalent voltage source? If I keep this open, pardon me?
So V Z12 by Z11 plus Z12.
Oh, how did you find that? If I keep this open, you see V2 equal to I1 Z21 plus I2 Z22. If I keep I2 open, I2 0, then this would be equal to I1 Z21. Now what is I1? Under this condition,
V1 by Z1.
V1 by Z1, and therefore this is V1 Z21 by Z11. Is that clear? Is that what you said? No, you said something else. This is it, V1 Z21 by Z11. All right. Therefore, our equivalent voltage source would have been V1 Z21 by Z11. And what would be the equivalent impedance looking back? Short circuit this. Then what is the impedance looking here? Oh, I am sorry, I should show this. You have to look at the impedance looking back into the network. So you short circuit V1. What would be the impedance looking back? What is the admittance looking back? No? You don't understand what I am saying? A two port.
1 by Z22 plus 1 by 1 by Z22 plus 1 by Z1.
So 1
No.
by Z12 plus
So
1 by
Z12 plus
Z11
Z22.
minus Z12.
No.
Z12 plus Z22.
It's much simpler than that. No. 1 by Z22 will be if this is kept open. Now I have shorted it. So I know the admittance, the definition of Y22 is the admittance looking back from port number 2 with port number 1 short circuited, and this is precisely what it is. 1 by Y22. This is the Thevenin impedance. Is it okay? No, it's not clear. Okay, what is Y22? Y22 is equal to V2 by, I2 by V2 with V1 equal to 0. So V1 equal to 0, if this is shorted, then the admittance looking here must be exactly Y22. Yes?
Yes.
And therefore the Thevenin impedance would be 1 by Y22. Is that okay?
So won't it be Y22 parallel with Y12?
No, nothing else.
No, Y.
Why? Because I2 equal to V1 Y21 plus V2 Y22, right? And if V1, if V1 is 0, then I2 by V2 is simply Y22. Agree? This is the definition of Y22, the short circuit admittance, driving point admittance parameter. It is the admittance looking into the driving point with the other port short circuited. So this is my equivalent circuit then. This is V2 and this is I2. The only problem is that instead of all Z parameters there is occurred in Y parameters, and we shall show later, because the Y matrix is the inverse of the Z matrix, Y22 shall be equal to Z11 divided by determinant Z, and that is how Z11 determinant Z, Z21 and Z11 will come in the calculation. Now it is a one loop network, nothing to, you see, V2 by V1 shall be simply potential division between these two. Okay. The input impedance, oh, that is a problem. Input impedance cannot be calculated from here. Is that clear? Input impedance cannot be calculated from here, because you have replaced the network to the left of this line. So you have forgotten what is happening at the input. Let me also show you a method of calculating the input impedance.
So can't we short circuit V1? So V1 will be 0 and V1.
Can't we short circuit V1? Yes, you are short circuiting V1. So
then
input impedance is here at port number 1. I cannot calculate it. But let me show you, it is not required for this particular problem, but let me tell you one way of looking at the network. Once again, another alternative way. The more ways you have, the better equipped you are. But an engineer's job is to find out which method will work best in a particular situation. In this situation it is not required, but suppose you are required to calculate the input impedance of a network terminated in a resistance, and there is no restriction on Y parameter or Z parameter or whatever it is. Okay? No restriction. We find in terms of parameters, then we make substitutions. Alright. I can look up on this network, be careful now what I am doing, no tricks, very simple method. I can look up on this network as an augmented one with an RL at the port number 2, okay, and then the output port is short circuited. Is that okay?
Yes,
All right. So this network, what are the Z parameters of this network? Z11, Z12, Z21. The only thing that happens is Z22 is augmented by RL. Agree? The Z parameters of this black circled network, Z parameters of N are given by the Z matrix, and the Z parameters of this is this. Now what is the input impedance? Input impedance is, for the augmented network, let us call this N prime. If for N prime, which parameter relates to Z input? Which parameter? No. No. Why? I have short circuited this. The port number 2 is short circuited. I am measuring the impedance at port number 1. So Z in must be 1 by Y11 prime. Isn't that right? The Z matrix is known, and I can find out Y11 prime. What would be Y11 prime? This will be Z22 plus RL divided by determinant Z, that is Z11 Z22 plus RL minus Z12 Z21. Isn't that all? Agree? y11 prime would be Z22 plus RL divided by determinant of Z. Okay. So, this is a inspection, you do no calculation, nothing, no simplification, and many a times you shall be required to do it. If you cannot figure this out, you will spend an hour over calculation of the input impedance. You must have all your equipments, all your tools at the tip of your fingernails, if you can. The final problem that will work out is that of the transformer, 9.7. 9.7. It says find the Z and Y parameters of the transformer, non-ideal transformer. The transformer is this. It is not a 3-terminal network. This is the transformer V1, I1, it is a truly 4-terminal network, no question of those 3-terminal equivalents. This is L1, L2, dots are here, and this is M. It says find the Z and Y parameters of the transformer shown in the figure, and then it says determine the T and pi equivalent circuits for the transformer in terms of L1, L2 and M. Obviously, the assumption is the T equivalent circuit or the pi equivalent circuit would hold when these two are connected to each other. Agree? This is the implicit assumption. Okay. Now, the solution. Is there any question before I give the solution? Now, it is obvious that if you write the two equations I1 SL1 plus I2 SM, the currents and the dots agree with each other, and V2 equals to I2 I1 SM plus I2 SL2, and therefore the Z parameters are SL1, SM, SM and SL2. Agreed?
So should we consider resistances also?
No, there are no resistances given. Non-ideal in the sense, oh, that reminds me, what is an ideal transformer? Why is it called non-ideal? Ideal transformer? Is that the only thing?
So L
No.
values are not tending to infinity.
So it's small one and
Correct.
L1 and 2
If K is equal to 1 and the circuit is lossless, no resistances, it is called a perfect transformer. Perfect. In addition to perfection, idealness is above perfection. Okay? Idealness implies that both L1 and L2 tend to infinity such that their ratio is finite. This is the definition of an ideal transformer. So, this is non-ideal, and you see the Z parameters are obtained by inspection, and you also know the if these two terminals are connected, that if it is a 3-terminal network, then these Z parameters can be represented by the T equivalent circuit, and the equivalent circuit would be L1 minus M, Z11 minus Z12, L2 minus M, and Z12 shall be equal to M. This would be equivalent to this provided this red colored connection is there, pink colored connection. Okay. Z parameter was simple. How about the Y parameter?
If this was not there, we cannot table it.
We can, because then physically this is not the same as this.
But then mathematically we can.
Mathematically is okay, so long as you work with only V1 I1 and V2 I2. But suppose this is a 10 kilovolt, the input is, what is this down conversion, 220 kilovolt to 230 volt, okay, at a substation. Suppose this is 220 kilovolt and it is ungrounded, alright, this is 230 volt and it is grounded, and you use this to calculate anything that you want, and you actually put your equipment in between these points, or you argue between this point and this point, alright, the whole house has had a fuse if not fire. fuse will blow if fire cannot catch before this, alright. So be careful in applying. This is why I used a pink color, I should have used red for danger, okay. The problem now is how to find the y parameters, and let me tell you, if you want to do it ab initio, then there is nothing better than using these equations. After all, what does finding y parameter mean? What does finding y parameter mean? It means that you express I1 and I2 in terms of V1 and V2. Okay. So what you do is find I1 from here in terms of V1 and I2 and substitute here. Okay. From one of the equations, find I1 in terms of I2 and V1 and substitute in the other equation. Okay. That should be simple enough. This is one way. The other way is you can, in this case, apply the T parameter equivalence circuit and apply definitions of the y parameters. For example, if I want to find out y11, L1 minus m, I am only doing mathematical calculation, nothing else, L2 minus m and m. Suppose I want to find out y11, then I have to short circuit this, alright. So I can calculate y11 by inspection. Y11 shall be equal to 1 over S L1 minus m. Why 1 over? Because I am calculating the impedance, plus the parallel connection of m and L2 minus m, which is obviously S m L2 minus m divided by L2. The parallel connection of two inductances L1 L2 divided by L1 plus L2, and since m and L2 minus m, okay, therefore this is 1 over S 1 by L1 minus m plus m minus m squared by L2. Agreed? Or is the simplification too fast? I have taken S out from both. M L2 by L2 is m, and m squared by L2 m squared by L2. So this m and m cancel, and you can see that this is L2 divided by S L1 L2 minus m squared. Okay. Alright. If this was a perfect transformer, what would have happened? Y11 would have been infinity. In other words, for a perfect transformer, the y parameters are not defined. Alright. Similarly, you can find the other two parameters, and I repeat, in this case you can apply the T equivalent circuit to derive the y parameters, because it's your limited objective, but do not dare to do anything else, because you might destroy whatever your transformer and also whatever you connect to. That's all for today.